All right, so I'm going to tell you a little bit about the work we're doing at Bedrock Systems, verifying industrial C++ code. So a little bit about what Bedrock Systems is doing. So modern cloud infrastructure is built usually on the idea of microservices or workloads that run on top of an infrastructure, some core infrastructure, which is usually Linux or and Kubernetes. And we usually think of these workloads as decentralized, but in practice, this decentralization occurs on top of a monolithic runtime, and that runtime represents a single point of failure where a compromised workload can compromise the underlying infrastructure and move laterally to infect and monitor other workloads. Bedrock aims to address this problem by providing security from a lower layer, a privileged secure layer that runs below the infrastructure. And there's a few benefits to this. One is that Bedrock Ultra is largely transparent to the infrastructure code, meaning that we don't have to implement all of the load balancing and fancy features that occur and are necessary for complex cloud deployments. It also provides a tractable verification target because we don't need to focus on all of that functionality. We can just focus on a small amount of security critical stuff. So the founders of Bedrock believe that it's very important for this underlying layer to be very secure, but it's really just a piece of software. And one way to establish trust in software is through proofs. And this is what they believe would be the best way to establish the highest guarantees about the security of the overall system. And the idea was really that this is especially important in the sort of cloud and connected sorts of environments where you have adversarial actors that are actively trying to take over the system. And the verification here is quite complex because Bedrock Ultra runs at a very low level, it's performance critical, and it's highly concurrent. And these are things that you really can't get away from in modern compute infrastructure. When we think about what does Bedrock Ultra do, we really need to give it a behavioral specification. Effectively, Ultra acts like the underlying hardware. So if the system is behaving as intended, it should basically run as if Bedrock Ultra doesn't exist at all. But as soon as it starts doing something outside of its parameters, something that seems wrong, Ultra should have the power to go in, stop things, remediate things, log things, etc. Now, I'm not going to talk today about the sort of remedial actions and whatnot that Ultra is capable of. We're mostly focused on the verification of the security aspects of this. And what I'm going to tell you about today is really our use of separation logic in the verification of this large system. And so you heard a little bit about separation logic in some of the previous talks. And I'm going to in particular, in this talk, I'm going to tell you about how we use separation logic kind of throughout the development lifecycle, during design, taking that into code, and ultimately stepping back and thinking about how does separation logic inform the verification of this entire system. So I'll start a little bit with the design aspects of this. One thing that we realized early on is that formal methods provides, and separation logic especially, provides more than bug freedom. So normally we think about verification as being, I've written my code, I want to ensure it has no bugs, therefore I will prove it. But what we found is that using separation logic to think about the design and kind of before the code exists allowed us to design code in a better in a better sort of way. And that gave us greater potential. And what we've seen is that the code that we developed with formal methods in mind has lived longer than the code that we developed without formal methods in mind. So longevity of code is influenced by the design, obviously, and formal methods and separation logic in particular provides a way to look at designs and understand how they'll work now and in the future. We had a lot of experience with systems engineers. At Bedrock Systems, formal methods engineers and systems engineers work closely together in the design, the coding, and the verification phases. And one thing that one particular instance where we saw a great amount of value is in the kind of complex relationship that Bedrock Ultra maintains with respect to the guest's memory. And the guest is operating on its own memory, obviously, but Ultra also needs a view into the guest's memory. And thinking about the concurrency patterns and the ownership patterns that are necessary to ensure that we do this correctly was very difficult. And here's a quote from our lead systems engineer. He said, basically, working through this in separation logic, thinking about it in that sort of way, clarified the problem and allowed us to kind of pull out the interesting nuggets and solve those in a way that has lasted through through many releases of Bedrock Ultra. This isn't the only instance where we've had this success. We've a variety of other places, and really more places than you could list on this slide. But there's a lot of places where people, not just formal methods people who are not trained with formal methods initially, have found a great deal of value from working with formal methods and thinking about the sorts of problems in using that light. So we think about separation logic as a lens for evaluating different designs, and we can carry those designs through the code and the proof ultimately. The last thing I want to tell you about this in terms of the social aspects of this is one thing I was concerned about when joining Bedrock was C++ is not something that we work with generally in academia. I have an academic background, and the way commercial mainstream C++ code is written is very different from the sorts of languages and work that I had done in academia. And I was wondering whether or not formal methods and software engineering best practices would actually align well. And I was pleasantly surprised that generally good designed, well-designed code has smaller and more natural specifications. This is not universally true, but we found that in a lot of instances, we don't fight with systems engineers. We actually say both identify a good design and both agree that it is a good design. And that's partially backed up by formal methods kind of being able to say it is a good design. There are two things that did trip us up kind of early on. One of them is it's very important to support idiomatic code. And initially we were looking at C++ is just a superset of C. Let's focus on the C. Let's focus on the C part of it. And we found that this was generally a losing battle because systems engineers who know a lot about software engineering and development are saying, the idiomatic way to do this in C++ is to use this feature and this feature. And when we didn't support those, that created a tension. And we found that we were often pushing for kind of bad code in the C++ sort of model. And by solving some of those problems early on, we were able to actually harmonize more with the way that systems engineers develop code. The other thing is performance, and it's often important to have good performance. And one thing that is interesting about performance is that sometimes the easy way to write it isn't always the fastest way it can run. And to get the verification of the faster code, you need fancier logics. You need the ability to express kind of more interesting protocols and stuff like that. So logical expressivity of your verification framework is crucial to being able to verify code the way the developers intend it to work. All right, so now on that last front, let's transition down into thinking about what this looks like in code. So we're verifying kind of modern-ish concurrent C++, and we aim for automated proof. So what does this mean? So you guys have seen some separation logic in previous talks, as I mentioned. At Bedrock Systems, we've developed a system called BRIC. It's a axiomatic formalization of C++. So we have given a semantics, or we've given a syntax for C++, which is derived closely on Klang's front-end semantics. It's very high level before any optimizations or anything like that have occurred. You're really verifying code. It's pretty much exactly the code you wrote. So we've given that syntax, and then the semantics is written directly in separation logic with weakest preconditions as axioms. So this rule here, WP operand cast L to R, is the way that variables are read in C++. It's an L to R cast. And you see that we're reflecting the program state, the program state in separation logic here. This T points to R fuzzy, which captures some of the low-level things that C++ has, using separation logic assertions. And we're capturing the behavior of the program itself using these WPs here, a different WP for each value category in C++. And we support kind of C++ 11 and generally up to like C++ 20 is the thing that people are generally using at Bedrock right now. In addition to the semantics, we've built a tool chain called CPP2V. And what this does is it takes C++ files as written by the developers and converts them to Coq abstract syntax trees. This is a very naive and simple transformation. We're not attempting to do anything smart at this level. And ultimately, once we have these ASTs in Coq, we can start writing specifications. We write our specifications directly in separation logic. Here you've got a simple mutex class. We're using custom Coq commands that we've written to associate specifications like this one with particular C++ code. Here, the enter call, the enter function of the mutex class. And you can see how separation logic works here. We've got mutex I and mutex R are kind of the sequential things that are owned by the threads that are accessing these mutexes. And then they're basically trading these contender tokens, which track the number of users, and mainly to handle things like integer overflow, and swaps those out for the resources that are protected by the lock. And the specification of exit is kind of the opposite here. So the nice thing here is we get unrestricted use of iris features for reasoning. We get to use kind of as much iris power as we need to satisfy our particular specification. And we can use Coq abstractions to wrap those things up so that clients don't necessarily see the underlying implementation and can reason about these things in a very abstract sort of manner. Ultimately, we want to take those specifications and connect them to the actual code, proving, for example, that the implementation of mutex enter satisfies that specification. And we do that using Bedrock automation. Rodolphe Lepigue is in the audience, and he is one of the main developers of this. But effectively, what this automation does is it takes two sources of information. One is language level reasoning principles, like what you saw in that WP operand cast L to R, phrased as what we call hints. And those hints are things that the automation will consume. The other place we get hints from are from the abstractions. So like mutex.r and mutex.i have interesting theory, implications, and things like that. And so we reflect both of those properties as hints, and then we ask the automation to kind of churn through the proof for us, applying those hints when they matter. And this approach gets us to verifications that sometimes look like this. These are particularly simple functions. And so we end up with completely automated proofs of them. Obviously, more complicated functions require some more work. But our automation, we've generally found, is pretty good at handling sequential code. And a lot of work happening in academia has shown that we can even push farther, giving actually quite good automation for concurrent verification patterns as well. So a little bit about how this automation works. So I'm not sure if you guys saw the IPM earlier, but the IPM is the Iris proof mode. It is distributed with Iris and is the standard way that people work with Iris. And above, you see a proof that was done by one of the developers at Bedrock, kind of in the Iris style. And I said, hey, look, there are a few interesting insights in here that are distillable and can be expressed as reusable hints. So we looked at this proof and we said, okay, here are those reusable hints. And so we phrase those reusable hints, we give them to the automation, and then the automation can discharge the same proof, proving the exact same thing in just one line. Because basically what we're doing is we're saying, hey, look, in many cases, the sort of verification is follow your nose. And in those cases, the automation is very good at following its own nose and finding the proof for you. All right. So now I'm going to take a step back and think a little bit about what does this mean as we're taking the verification of these individual functions like mutex enter and mutex exit and really building them up to think about the verification of this entire Bedrock Ultra platform what does that mean, and how does separation logic play into that? So the first thing I want to talk about is the fact that separation logic is a nice formalism, but it's very language agnostic. So separation logic provides things like separating conjunction and things like that, existential quantification and things like that. But it doesn't think a lot about like what the structure imposed is really just the structure of resources. And those resources can come from many different places. So here on this first line, I'm looking at the invariant that backs the semaphore implementation, which backs the mutex implementation in that example that I showed earlier. And you see that the first bit of this assertion is really talking about C++ state. So this is program state that you'd normally think about, hey, I'm verifying a C++ program. I should see C++ state. And that's obviously very important. But the next line actually here is state coming from the operating system. So it's not state that's built into my C++ program. This is state exposed to us by calls to the underlying hypervisor. And in this case, the hypervisor is providing an additional layer of semaphores that's integrated with the hypervisor scheduler. And the invariant here is tying the state C of our C++ program to the state of that underlying hypervisor semaphore through the use of a bunch of logical ghost state. And this ghost state looks complicated, and it is to some extent somewhat complicated. I'll tell you that the majority of this is due to the fact that you have to be able to deallocate semaphores, and this tracks things that are necessary for deallocation and for finite integer arithmetic constraints of C++ and modern hardware in general. So this kind of shows you that separation logic can apply at more than just kind of a single program. We can start applying it and mixing resources from different places into similar abstractions. And remember, when we saw the mutex invariant, a few slides ago, we didn't know anything about the hypervisor. We didn't know a lot about these sort of underlying ghost state, and all of that has been packaged away so that users of the mutex abstraction think only at the high level, and implementers of the mutex get to think at this low level, but they still share a common sort of verification paradigm, the separation logic. All right. So we've seen all of the uses of separation logic that we've seen so far are uses of it to talk about implementation level resources, things like the values in memory, the values in my program. But we can also use separation logic to express the specification itself. And that allows us to prove behavioral refinements of what we said we wanted to prove of Bedrock Ultra using separation logic without leaving the separation logic paradigm. So on the left-hand side down here, this is code that's running in an earlier version of Bedrock Ultra. It's a verified console multiplexer, so you can go in this terminal and say, I want to talk to application number 1 or application number 2, and it'll start forwarding your messages there. And so it has this admin console, and then it has clients, and then it redirects you based on that. And on one side, it's connected to clients, and on the other side, it's connected to an underlying UART driver, which is also verified. And we give this whole application, so this UMX, this blue box here, gets this specification up here that says spec of the initial state of the UMX entails WP of main. This is a slightly simplified, but morally what we're proving is something like this. And when we prove that, we're able to extract a refinement that says running this program will always behave, kind of its IO behavior will always fit in the IO behavior allowed by this UMX LTS. So I'll tell you a little bit about how this works in a little bit more Coq code. You can define in Coq relatively easily a labeled transition system for this UMX. It's got 4 pieces of state, nothing particularly interesting here. And its initial state down here, as what you saw, this is how it starts. You describe the transition system via this step relation, and that tells you how should the state evolve as, for example, messages or characters are received from the input or the output. And then ultimately, the implementation of this is in C++. It's a concurrent program. It is segregated into a control and a data plane. The data plane itself is further segregated into an input loop and an output loop due to restrictions of the underlying hypervisor. And all of these things communicate via these concurrency protocols that you saw in earlier talks. We've described these concurrency mechanisms in separation logic, and then we carry out the proof using that. So a little bit about how this works at the high level. So main gets this obligation to act like the UMX. So that's expressed up here. And that's just kind of the cookie cutter sort of solution we have. If you want to verify an application satisfies some behavioral specification, we know what its specification is. It looks like this. And everything else now is internals of the proof of the UMX. In particular, what you do is you take that monolithic state and you start breaking it down using separation and establish four lower level resources, one for the active client, and then one for each of these buffers that exist in this state. Main is going to set up its various data structures and invariants and whatnot. And then ultimately, it's going to align all of these resources so that the main thread of the input loop gets to use this. And so the input loop runs as if it's the only thing running because it has all of the resources. But as soon as you transition to forwarding to interacting with one particular client, the division of these resources changes across different threads. And we need to know that both threads agree on the active client and that there are mechanisms in separation logic like fractional permissions and whatnot that allow us to relate those things and guarantee that these threads have a consistent view. But we also get the ability to transfer, for example, the toUart ownership to the output loop. So it gets to work with the UART, kind of knowing that it doesn't need to worry about any interference from other threads, even though other threads are running at the same time. And the same thing is true for this input loop. So this enables us to give a fairly modular specification and modular verification of this application, ultimately deriving this kind of interesting property around behavioral refinement. All right. So that's the end of the talk. What I basically told you about is how we've used separation logic, kind of we've applied it in industry, thinking about how we use the same formalism to go from designing, conceptualizing the way we design classes and things like that, carrying that down into code, thinking about the verification of concurrent C++, and the proof automation that allows us to verify the actual functions against their specifications, and then finally, thinking about what that means at the higher level, connecting code up to the overall system specification, how we can do language agnostic and multi-program verification, providing kind of very interesting and powerful properties like behavioral refinement. So with this, I'll take questions, and thank you very much.